ball deform into a particular shape, and you see it's a worm-like shape, right? It's elongated. And I'd like to explain to you why that happens, right? But before I do that, let me start by just introducing to you the title, right? The title includes two sort of concepts that may be familiar to you. One is active matter, which we've heard a lot about. And the other one is elastocapillarity. And to introduce that, let me just play you a video of this experimental system. What happens in this experimental system is that you put a droplet of water on an elastic surface, and due to the effect of the surface tension of the water, you see the surface deforming, right? And so this idea of the interplay of surface tension, right, or capillary effects with elasticity is what people generally call elastocapillarity. But let me be a little bit more precise about it, right? So when we think about surface tension, right, one of the first things that comes to mind is the idea of droplets or bubbles, right, fluid surfaces. And we know that, for example, in a bubble, the effect of surface tension is to always favor a spherical shape, right? The bubble is a good example of a surface tension force, but it doesn't have any elasticity, right? So it's not there are no elastocapillary effects. Another example where we have this interplay between surface tension and elasticity that I won't be talking about today are shells, right? Usually in shells, in fact, we don't call it surface tension, we just call it tension because the entire system is a surface. And this is something like a tennis ball, right? You can, a tennis ball is hollow, and you can think about applying tension to it and seeing how the shape deforms. What usually people think about in terms of elastocapillarity, though, is a different type of solid, right, which is not thin, right? You instead have a bulk solid, and on the surface of this bulk solid, you have some sort of a surface tension force due to the interface between the solid and the fluid outside of it. And for most solids, or for example, for a piece of metal, that surface tension is too weak to really affect its shape. So we don't think about elastocapillarity in that context. But for something like a gel, the surface tension becomes big enough to actually deform the entire shape of the object. And that's what you see in this picture here. You start out with a cylinder of gel, and due to the effect of the surface tension on this cylinder, you have this instability, the formation of beads, right, that are all sort of approaching a sphere, right, favoring a spherical shape, but there's some sort of competition with the gel elasticity that gives you this interesting, modulated, beaded geometry. So these examples are examples of what might be called passive elastocapillarity. And what's important here is this constraint of equilibrium that tells you that an interface, any sort of equilibrium interface, will have a positive surface tension, right? So in one of the first things that you can do when thinking about active forces is to try to break this constraint, right? And so in to phrase it in other ways, right, we know that in a passive medium, a positive surface tension will always favor the same shape, no matter what shape you start out with, right? No matter what your initial geometry, if you have a positive surface tension on the surface, you will always want to go towards a sphere. But in an active solid, you can have active stress contributions that drive the overall or the effective surface tension negative, right? I'll talk a little bit towards the end of the talk of how you might realize it experimentally, but the idea of an active surface is not new, right? You can put all sorts of motors on the surface to make the area want to locally expand, and that's what drives the surface tension negative, right? So if you think about covering a rubber ball with motors and driving the surface tension negative, then you can ask a very fundamental question here, which is, if you start out with a sphere, right, what shape do you go to, right? And unlike the passive case, where the shape is always the same, here, the shape that is favored will actually depend on the material properties of what your sphere is made from. And so this is something that you can solve exactly in linear elasticity, right? So you add a negative surface tension to a sphere, to a solid ball, and you get this sort of phase diagram here, right? And what you see on this phase diagram are two axes. One, the horizontal axis, is just an axis of passive elasticity, right? It includes both a surface elasticity term and a bulk elasticity, or a shear modulus. And their ratio is what determines this horizontal axis. For the vertical axis, you instead have this active component, right? So when the surface goes unstable, that will, the activity you need to destabilize this entire solid, that will depend on your active driving. So what this phase diagram tells you is that by controlling just the passive capillarity, you can control what shape you go unstable towards, right? And there's a different set of shapes going from this, uniaxial deformation, which you can call L is equal to 2, to these much finer structures. And you can contrast this sort of shape change for a 3D object due to active surface driving with other mechanisms. So for example, one common shape change mechanism is the buckling of shells, right? There, of course, that corresponds to having a zero shear modulus inside of the shell, right? There's no bulk elasticity there. And that corresponds to this limit, right, going to the top right part of the phase diagram. So you don't have this control over shape in the same way. And another common limit that people have taken before is to look at wrinkling, right? Wrinkling is kind of the opposite limit to shell buckling, in that it corresponds to a small length scale, which also corresponds to a large shear modulus. And there you no longer have a bulk shape change, you instead have a patterning of the surface, right? You have small wrinkles on top of an overall spherical shape. What active elastocapillarity does, in contrast to both of these mechanisms, is that it gives you this ability to tune which shape goes unstable and which shape you see by tuning the shear modulus, right? That's the new knob that you have here. All right, so this is the linear theory of elasticity, but linear elasticity is not everything, right? And in particular, this sort of stability analysis that I showed you doesn't actually give you the final shape that you see for this object. And in order to get a final shape, we have to go beyond the linear solution and to look at the effects of nonlinearities. You can't do the full solutions exactly. So I'll instead pick a particular mode and make some approximations to show how in principle a final shape can be determined, right? And the mode that I will pick is going to be this L0 mode, or uniaxial deformations, where if you start out with a sphere, you can get two different shapes, right? One shape that you can get is a flattened pancake if you sort of compress, squish the sphere. And the other shape you get is an elongated or worm-like shape. So I'll call this type of shape a worm, and this type of shape a pancake. They're both just ellipsoids, right? And so what we want to do is to solve this nonlinear theory now. And the approximation we'll take is we'll assume that this elastic deformation will be uniform throughout, right? And then we can write down an effective free energy in terms of just one parameter, this deformation lambda, right? If it's greater than 1, it's elongated. If it's less than 1, it's compressed. Minimize this effective energy and see what comes out. So in order to do that, we of course have to specify this elasticity. The dilation is the same that's already given, but to specify the elasticity, we have to pick a nonlinear theory, right? At linear order, we just pick a Hookean theory. We augment it with what's called a neo-Hookean term that still only contains the shear modulus. But then if we add a material nonlinearity, then we get an extra parameter for nonlinearity. And we pick a specific model. If I have time towards the end of my talk, I'll mention why this particular, why this choice doesn't matter so much. But the idea is that this simple model called the Mooney-Rivlin theory has a single parameter that lets us tune nonlinearity, and that has an important effect. So what is the effect of solving for the equilibrium shape with this nonlinear elastic model? Well, you see a sort of phase diagram here, right? Now, I still have on the vertical axis this activity, right? The effective surface tension. And now on the horizontal axis, what I have instead is the nonlinearity, right? In fact, the ratio of the nonlinear to the linear elastic terms. And what you see overall in this phase diagram is that you can actually tune between all of these three different shapes, right? You have, for low active driving, the sphere is stable, as we know from the linear theory. And then at the nonlinear term picks which of the two shapes you get. You get either a pancake or an elongated worms. These three shapes are separated by a snap through or discontinuous transitions that all meet at a critical point. And in fact, the presence of the critical point is what suggests that there's something universal in the shape of this phase diagram. But before I discuss that, let me first compare this theory, which includes a lot of assumptions, with some simple numerical simulations, right? So the theory, of course, is continuum. The simulations are not. And we want to not only discretize this theory, but instead build a microscopic model, right? And so the way that we can build a microscopic model for active elastocapillarity is to start with this bulk orange mesh of passive springs that just gives you a solid, right? And cover it with active springs on the outside. These are the blue springs. And all that the blue springs will do is that they will try to expand, right? All of the springs have these active stress elements in it. And by expanding, they will try to overall expand the surface area of this ball and therefore lead to a negative surface tension. And I'll just mention that you also need to include in the simulation bending energy of the surface by including bending between the sort of surface plaquettes. And so this is a very minimal ball and spring model. It has only a few terms in this effective energy, and it's sufficient to demonstrate our results not only qualitatively, but also quantitatively, as I'll show you. So let's start out with an example on this phase diagram that I showed you before, where you have a transition between a sphere and the worm. And this is exactly the video that I played to you in the beginning of this talk, right? So you start out with a sphere. Once you drive it sufficiently, you increase the active surface tension enough, it will deform into a worm. And that's because we've started with a material that has a high elastic nonlinearity. We can also compare this numerical simulation with our theory, right? And the way we compare it, essentially, we match the location of this critical point in the simulation and the theory, and then plot the deformation as a function of activity, right, for different values of the nonlinearity parameters, right? And so in this orange example, right, this is the simulation is given by the orange line, and the theory is given by the dashed line. And you see that, not too far from the critical point, they agree pretty well. And then there's maybe a little bit of a deviation once you go sort of deep into the worm-like phase, when the nonlinearity, the precise model of nonlinearity becomes important. And you can reproduce this agreement with other parts of this phase diagram. So for example, if you start out with a pancake, low nonlinearity, you'll form a pancake-like shape. And again, the theory and the simulations seem to agree pretty well. But perhaps the most surprising part of the phase diagram is the one just to the right of the critical point, right, where you have a particular slope for this transition between pancakes and worms, and therefore you can snap through twice, right? What you see here following this line is that if I play the video, first you make a worm, and then the worm snaps through again to a pancake. And this is again what you see in this simulation sort of graph, where you first start following so snap through and start following the worm-like shape, and then snap through again and follow the pancake-like shape. So in this way, you get agreement between the theory and simulation, both in terms of the shape of the phase diagram, but also the quantitative results that you get. So I have just a little bit of time left, so let me kind of race through it. I mentioned that this is something generic, right, that happens for spheres. In fact, this phase diagram has the same shape for any spherical top. So any shape that doesn't have an anisotropy axis. So that includes, for example, all of the Platonic solids. The other case that you might consider are uniaxial shapes, and they're a little bit different, right? If you start out with a worm and you add this active driving, you won't snap through to a worm, you'll deform continuously, right? There will be a critical point, but there will be this space of deformations. And similarly, if you start out with a pancake, you can smoothly deform with to a pancake, as well as go through a snap through transition, depending on the parameters. What's interesting here is that if you plot this phase diagram a slightly different way, where the initial anisotropy is on the vertical axis and the activity is on the horizontal axis, you'll find something that kind of looks like the Ising model. And there, the Ising model phase diagram, right, where you have the magnetic field on the vertical axis and the temperature on the horizontal axis. And the reason for that is because you can write down an expansion near the critical point that relies only on the symmetries of your system, and the types of terms you get are different, right? Whether you get a linear term in this expansion depends on whether you start out with an isotropic shape or not. In other words, the linear term acts like a magnetic field, and the rest of the terms act like a Landau free energy for the Ising model, which is why having this Landau expansion is why we believe that this shape of the phase diagram is generic, right? All right, so I promised at the very end to get to this idea of experimental realizations, and I already mentioned briefly the idea of just covering a rubber ball with some motors, right? You can make motors that act as dilations, or you can cover it in some sort of active origami. I think that there are probably a lot of interesting biophysical mechanisms for this type of active elastocapillarity. For example, cells that have a cytoskeleton and they've had negative surface tension measured in the membrane. But I'll focus on the smallest of these scales, which is at the nanometer. there's this particular work that has inspired us that where we've collaborated with Tom Wilkes to try to understand what happens in a particular system of spherical nanoparticles as they deform. Right? And these nanoparticles, they're elastic in the bulk because they're made out of long polymers that are entangled. And the special thing about the system is that the polymers are made out of nucleobases, right? They're components of DNA repolymerized with a different backbone. And what they do is to put these nanoparticles in a solution of complementary nucleobases that are much shorter, right? So they only penetrate the surface of the nanoparticles, and because they want to insert themselves, they expand, right? And they expand the surface in particular. And if you expand the surface of an elastic particle, you get exactly the active elastocapillarity effect. This is exactly what they see in experiment. They start out with spherical nanoparticles and they end up with worms, right? And one of the interesting questions we have for this particular system is why they only ever see worms in the experiments, right? Perhaps there's a way to, in fact, tune this system based on elastocapillary predictions and generate pancakes instead. All right, I'll wrap up here. I wanted to advertise just a couple of things before I finish. One is the poster on Gather that my PhD student is presenting on something completely different, having to do with active fluids instead. Please come find him. And the other thing is that we have an assistant professorship open currently in Bath Physics. So I think I'm out of time. So I'll leave this conclusion slide up and I welcome your questions.
Okay, thank you, Anton. It is time for questions. So we have a question from Thomas. Thomas, if you can unmute yourself.
Yeah, so lovely. So if I understand correctly, you have this discrete element type of a model of an elastic solid with these spring networks. I'm just curious about if you have to take care, we've used similar things for studying like material processing fracture, and we had to work really hard to get rid of residual stresses, make sure all the springs are at a length they're happy with in the disordered network. And I'm just curious, and it made me wonder about like residual stresses in a system like this and how they influence things.
So this is a very good point. So I think we've lucked out in some sense in the numerics because we have this, critical point, right, and this sort of universal theory for it. So we don't have to work too hard to get quantitative agreement. And I think that's only because of that, right? Otherwise, we would have had to work much harder. But the basic idea is that we have in the bulk, right? When we start out, we have all of the bulk springs relaxed, right? So we don't have to worry about stresses there. And then the active surface springs, we sort of set them again artificially to have all the same stress, right? That they exert. So in some sense, it's kind of designed to have the same kind of phenomenology, right? That we had in the continuum. I don't know if that sort of answers your question.
Yeah, thanks.
Okay, Jan, you have a question as well.
Yeah, thanks. Very nice talk. I had actually a related question, and it was about these surface springs. And what role plays the initial triangulation that you basically said? Because I saw in your video that, especially in these, I think, pancakes or these worm shapes, then there are regions where there are extremely stretched bonds and others where it's not. Well, for a different initial triangulation, you might even get a different shape, but definitely different distribution of these stresses at the surface.
Yes, I agree very much with that, that there's some effect, right? So this, we showed what makes for a nice video, right, of these springs is where the mesh isn't too fine, right? So we can, once you increase how fine the mesh is, that effect should be, that effect goes down somewhat. But I agree with you that there's still some effect of triangulation. We, quantitatively, right, what we see is that when things are nearly spherical, that effect seems to not be so big, right? Because everything kind of starts out uniform. And then when it starts to become very flat or very elongated, then that effect starts to matter, right? And that's what in part, I think, why our agreement with the continuum theory starts to break down in these large deformations. So I agree that for large deformation, that becomes much more of an important point.
Yeah, thanks.
Beno, you have a question, last question.
Yeah, hi. So I was wondering if you could specify a little bit your comment you made that you think that your phase diagram is pretty generic.
Mm-hmm.
So you mentioned that the fact that you can formulate a Landau theory,
yep,
locally, basically, makes it generic. So this I didn't completely get, because I mean, such a Landau theory you can formulate pretty generally, I think. So cases where you could not formulate such a theory locally would be rather exceptional, I think. So I don't understand how.
So when what are exactly the kind of conditions, right, to that let us write this out, right? So Landau, I think I think it's a very good question. Of course, I skipped over any of the technical details, so thanks for asking me to clarify. But the basic idea is that this form of Landau theory, right, without an anisotropic term, this predicts the existence of a critical point, right? As long, and in that sense, the basic ingredients are very general, right? In order to, one of the important points here is that you need a nonlinearity that comes in its lowest order, right? So this W, right, for example, doesn't might not exist. So for one example where it doesn't exist is if you had a 2D shape, right? So you had a disk surrounded by a line tension, right? That's an example where you get a different type of Landau theory, and the phase diagram no longer looks like this, right? Of course, another point is that you need, in order to get this critical point, you need this R to change value, right? So you need this system to have a linear elastic instability, right? That's what the R changing value corresponds to, and that's what the exact linear solution tells you. So I think these are very, these sound like very general ingredients, and I think that they are, which is why, I mentioned that this phase diagram seems to have a generic shape, but it's not, it does have a few of these important ingredients in it.
Okay, thank you.
Okay, we are kind of late, but I have a question myself.
Yeah, please.
that I wanted to ask. So could you imagine increasing the drive enough such that you have a change in topology in your surface? So imagine making 2 drops out of 1 drop, just by this active tension.
So I mean, that's a really good point. I think that's a very interesting question. Of course, that's not, it's not taken into account with our model, right? It tends to happen, right? It tends to happen very naturally in fluids, right? If you think about increasing the area of a micelle, right? They actually, the way that happens is that the micelle splits up, right? It doesn't just, try to grow or deform into a cylinder. So that's a mechanism. But I think it would be really interesting to see how that might play out in elasticity, where have things like fracture, right, and other mechanisms that have to come in as well.
Okay, thanks.
Yeah.